Hello everyone, once again, welcome to Electrical Measurement and Measuring Instrument lecture. This unit continuing toward the analog voltmeter and ammeter measurement units. First, we have to be clarified regarding galvanometer in this particular lecture 1 of unit 2, where we have two type of galvanometers. First is ballistic galvanometer and second is de-Arsenal galvanometer. Here we have give the precisely what is about its theory, its working principle and its construction perspective. Now, as we regarding the ballistic galvanometer, as you see in your right hand side, there is a pictorial view of a ballistic galvanometer, which will measure the electrical charges obtained from magnetic flux. Its construction is morely familiar to the moving coil galvanometer, which is it contains very small electromagnetic damping and it is contains some undamped oscillations also. Mainly regarding the working of ballistic galvanometer, as you see in your right hand side, has a permanent magnet north and south pole in which iron core is placed between them, having some moving iron coil over it. And we starting, it states that whenever charge measured by, as we seen that charge is measured by this basically ballistic galvanometer, when passed through some coil, the coil start moving. When the charge flow through the coil, it give rise to the current due to the torque produced from the coil. It is basically a relationship how the particular current flowing this particular moving charge and its relation with magnetic field across the north and south pole. The torque contain both the quantities. First is current in our particularly moving coil, and second the magnetic field B. And the torque production is equal to B I A N. The product is basically of torque and time period produce a force, which is essentially initially a kinetic energy of a coil, complete used in doing the work, and it is moving back to the original position. Basically, this coil oscillate in the magnetic field and deflection is noted from the charge, which can be calculated. As you see in the construction perspective part, as we given below, the working principle, which will give the how the particular ballistic galvanometer move, is given by the motion of by interaction of electrical current or the charges in the moving coil and the magnetic field due to the permanent magnetic field. There is a force could be occurred by using the Lorentz force. Okay, the construction wise, as you see in the previous fundamental, as we see in the regarding d-also meter and the normal galvanometer, the readings are being used by the indicating meters. But in this particular special type of ballistic galvanometer, the mirror are being used for the indication of your values. Here you having some mirror, okay, and having a phosphorus bronze wire, which will use for connection of a torsion head. It is a fixed head to the mirror and which will be continuing attachment to the moving coil, which will be carrying the current, and again through the spring coil going to the external field also. This particularly galvanometer contain the rectangular coil of a copper at 10 to 150 meter turns. As you see, it is a basically a concave pole piece of strong magnets, which is providing the sufficient magnetic field for torque to rotate per mirror, in particular your ballistic galvanometer. When the coil is rotating, this magnetic field and EMF is induced as by the Lenz law, and this it as we know, the Lenz law opposes the motion of the coil and is known as electromagnetic damping. This minimization of damping should be wound by the wooden frame. Whole suspension system is provided in glass spaces also. Now, as we know the construction and working both of the type, now we move toward the theory of this ballistic galvanometer. Let us assume there is a n number of turns are in uniform magnetic number of turns of a rectangular coil and is placed in a uniform magnetic field. Let L and B are the length and breadth of the coil. Then area of the coil should be A equal to L into B. Then that torque provided, as I say you, it is a Lorentz force NIBA. Then the for a very short durational time, this torque should be NIBA by dot dt for short duration of time. There is some oscillative or periodic motions have been there, which will be uh, that is unoscillated movement, which will be break down by the electromagnetic damping in this particular case. As we saw that the current passing for a small time period t, then we'll give the integrative part, integrate the torque equation by 0 to t for a small fraction of time. Then our equation to be NABQ, which is proportional to charge flowing in this material. As we know, we have to find out the number of charge flowing in the particular circuit. Then by the function of angular momentum, this is I multiplied by omega. Angular momentum of coil should be equal to the force acting on the coil. So from the above fourth equation, we will get that I omega, which is a torque provided, it is angular momentum is equal to NABQ, where K is the kinetic energy deflected the coil through the angle theta. Then the deflection is distorted to the spring. Then restoring force that will restore the particular R deflection mirror from its to the original position is given by half of C the theta square, and the kinetic energy which push the particular mirror to is some angle theta given by half I omega square. This as we say, this restoring force and this kinetic or deflection force should always be equal at the steady state. So half C theta square equal to half of I omega square. So that gives the equation of periodic oscillation, that is T equal to 2 pi root of IC, that is equation number 10. As we put this equation number 10 into the perspective of whole squaring nature, this will give our 11th equation T square C upon 4 pi square by I, and this by providing the 11th equation and 9th equation, we will have T square C square theta square 4 pi square into I square omega square. And finally, by putting the omega from the fourth equation, as we put in the initial equation, I omega is equal to NABQ, we will have this equation where Q charge number charges, so providing from the particular electromagnetic coil is given by Tc theta upon 2 pi NAB, where we assume K as a constant quantity. Okay, then it is basically a reduction factor of galvanometer from given above. Then Q charge is directly proportional to deflection of torque. In the particular ballistic galvanometer, we will say amount of charge passing through coil is directly proportional to deflection of charge. Basically, also we said that the scale of this ballistic galvanometer is linear in nature. Okay, so one or more thing, that is charge and sensitivity. Sensitivity is one of the important factor which is relies upon the output upon input of the factor. As we say, deflection is our output and charge is our input. So we will have the equation of for the ballistic galvanometer, that is NAB by C equal to 2 pi t, but is our eighth equation from for the charge sensitivity, where charge sensitivity of a system can be realized by, or a current sensitivity, how the current sensed by a particular instrument and will deflect in the ballistic galvanometer given by NAB upon C. Okay, so we will say the charge sensitivity is 2 pi t times of current sensitivity. Okay, so that is this particular relation will be helpful in various stated numericals, as we see in uh, earlier numerical, that is what again do in our particular class also. Okay, thank you so much for this particular lecture. We will continue our second lecture for de-azimuth galvanometer.